Hi everyone, we are moving on away from physics and into chemistry. So I hope you enjoyed the physics topic about space and energy, and that you've had a little look at the sky. Some of you have emailed me to tell you that you saw the International Space Station going over. So I know some of you watched the astronaut launch live, and hopefully everyone's watched it since from last week's lesson. And I don't know if any of you saw the strawberry moon. To have to be honest, I didn't really notice much difference, but there's lots going on with space stuff. Just keep an eye out. There's lots of things if you want to know how to find out what things are coming. There's various things you can follow to find what's going on with space if you're interested. So just drop me an email, I'll tell you how to do that. Okay, so we're moving on to chemistry, back to the kind of fundamentals of chemistry that we've already started. So if you remember, we did a topic in January, I think, February time, about chemistry, and we were learning about separating mixtures, we were learning about techniques, we were learning about particles. And now we're going to move on a little bit from that, and we're going to move into types of particles called atoms, a little bit about the periodic table. And the idea of this topic really is to kind of start looking at some chemical reactions. And then when we move through into year 8, you do a lot more in-depth work about atoms and the periodic table then. But I'm going to try and introduce a few keywords to you today. So you should have this knowledge organizer already. This is the one that I'm going to be using for the next few lessons. But if you don't, I've put one in the folder for you. So we're going to be having a look at, I think I'll do purple. Today we're going to look at metals. We're going to look at non-metals. Oops, I'm not circling that very well. We are going to touch on this reactivity as well today. I'm going to talk about water. And I think for today that's kind of it. I am actually going to touch a little bit within reactivity at the end on this diagram here as well, but this is something that we come back to a few times. So those are the kind of areas of the knowledge organizer. So just a note on this, there's some words here, things like this: malleable, ductile, brittle, that you may not know, and I'm going to go through those words in this session, so hopefully you will know what those mean at the end. But it's really important that you start to come back to this knowledge organizer. It would be a really good idea today if you kind of start to at least learn the definitions for these 4 that I've circled on the left, and it might also be a good idea to learn some of these facts at the bottom. Okay, so learn the facts as well. So you might want to do some self-quizzing or just some form of learning of these as part of your task later. Okay, so let's kick off. We have got 2 words here: atoms and elements. So an atom is a type of particle. Okay, we've talked, I'm sure you've heard the word atom before. You might not understand quite what it is. We're not going to go into detail about what's inside an atom or how atoms are different from one another. But what you need to know really at this point is that they are a particle, they're a type of particle, and they come in lots of different types of different forms. So for example, there's 4 there: carbon, gold, silver, oxygen. Those are all types of atom: carbon atoms, gold atoms, silver atoms, oxygen atoms. You've heard there's loads more: hydrogen atoms, iron atoms, nickel atoms, copper atoms. They're all different types of atom, but they are in fact all atoms. Then, if we have a substance that's made of only one type of these, then we've got an element. Okay, so at the bottom here you can see there's some pictures. This one here on the left, that is some gold pieces. So each of those chunks are made up of gold atoms. So remember, we're now talking about very, very, very small things as opposed to the universe, which is very, very, very large things. So we're back on the atomic level. So if you were to look at your gold, drawing this very well because it's quite hard to draw on a screen. There we go. So this is a solid. If we remember, solid atoms or particles are going to be in rows. They're going to be quite rigid. They're going to be vibrating in position but not moving around. If we were to look with some incredibly amazing X-ray particle glasses and we could see the particles of gold, we would see that each one of those particles was a gold atom. There would be nothing else in there. It's pure. Okay, and we did the word pure last time. Only one type of atom. It's pure gold. Okay, this one here in the middle is another metal. It's called magnesium. And again, if we were to look at it, we would see solid. And so we'd see the solid layout of particles, but this time all of those particles would be magnesium atoms. Okay, nothing else in there. Finally, this is a gas. It's called bromine. It's a non-metal, actually. I'm going to talk about that in a minute. And the reason I've chosen bromine is because it is a coloured gas. It's like a brown colour, so we can actually see bromine. And if we were to look at the particles again, we wouldn't see that layout. We'd see more like this because it's a gas, so they'll all be far apart, whizzing around, but they would all be bromine atoms. There wouldn't be anything else in there because these are elements, so only made of one type of atom. Okay, so let's move on. So within our elements, okay, and there are a certain number of elements in the universe. I think it's something around 118. And you can find not all of them, but some of them in your planner, in your periodic table. Now we can divide them, well, there's various categories we can divide them into, and actually is when we do our whole year 8 topic on this, you'll see that there's more than just 2 categories. But there is one way of dividing them into 2, and that is to divide between metals and non-metals. Now, I'm sure you're quite familiar with the word metals, and if I gave you a substance and said, is this a metal, you might well be able to tell me, because you already kind of have learned over time and through your life what a metal looks like. So if we take an example like a gold ring that you might wear on your finger, we've got a metal which is shiny. Okay, so they tend to be shiny. Sometimes they might go a bit dull, but if you polish them up, they'll go shiny again. Now, they are good conductors. And what that means is they're able to transfer very easily these 2 things, heat and electricity. So heat we've already met. We talked about that when we were doing the energy topic. Electricity we touched on as well. Both of these things are able to pass through and move through metals very easily. That's what we mean by good conductors. Then we've got the fact that they are malleable and ductile. Now, malleable is an interesting word. Basically, it means can be hammered into a position. So to give you an example of that, if you think about blacksmiths making horseshoes, what they do is they'll take the metal, which I think tends to be iron, they heat it up and then they bang it with a hammer into the shape of a horseshoe. That's because the metal is malleable. It's able to be hammered into position. Sometimes you don't need to heat up metal to be able to do that. Some metals are quite soft anyway, but some of even the very hard metals can be heated up and then made into shapes by hammering because they are malleable. The other word here, ductile, sometimes is used interchangeably with malleable. Some people use it to mean the same thing, but what it really means is that you can make it into wires. You can get a piece of metal and you can make it nice and thin and you can kind of stretch it out and it will form a wire. Okay, so if you think about your phone charger, inside of the plastic, you will have probably copper wire, and copper is able to be made into a wire because it is very ductile. Okay, it can kind of string out to very thin without breaking. Why is that in your phone charger? Because it's a good conductor of electricity. So you can get the electricity from the socket on the wall into your phone. Okay. Now, non-metals then are kind of opposite to this. So they don't tend to be shiny. They tend to be more dull in appearance. They are bad conductors of heat and electricity. Some of them can conduct it a little bit, but generally they're a lot worse. You wouldn't use them to make a wire, for example. So many of them are what we call insulators, meaning that they don't conduct heat or electricity very well at all. Okay, now brittle is the kind of opposite to malleable. Okay, so if you think about a glass milk bottle, if you smash that with a hammer, then it is going to smash into lots and lots of pieces. Okay, it's not going to be malleable and able to be hammered into position. It's just going to break. It's going to splinter. So that's what brittle means. Okay, so it is. What should we say? Smashes easily. Okay. Right, let's leave that there for the time being. Now let's have a look. It would be not great to mention this at least. So in your planner you'll see the periodic table of elements. It might not be a complete one, but it will have a lot of chemical elements listed in it. And you can see on this picture at the top there are different colours, and those different colours are denoting like different sections of the periodic table that we're not going to go into in this topic, but we will do next year. But you can see all the elements in there have got their own symbols. This one's not great because it doesn't give the whole name as well. Probably your planner one does. But to take an example here that I've just circled, Mg stands for magnesium, and it is a kind of universal code. So if you use the symbol Mg, it doesn't matter where you are in the world, you'll know, people will know, chemists would know what that was. Okay, and this is all the elements. Actually, this is a slightly decreased version because there are some very odd elements that at the bottom that we don't necessarily include. But this is the majority, let's say, of the elements. And so everything else on the planet is made up of these elements in different forms. And we're going to move on to that in a second. What I really want to mention about the periodic table really now is, at a very basic level, you can split it into two bits. Okay, and you can see here at the bottom we've got two bits, the metals over on the left and the non-metals over on the right, and you've got this kind of staircase divide between them. The non-metals here on the diagram are in orange and the metals are in like a bluey teal colour, and that pretty much is the rule: left for metals, right for non-metals, with the exception of this one over here, just to be awkward. This is hydrogen. You can see it at the top here as well. Hydrogen is a non-metal, but is found over on the left. It's the only one that doesn't fit the pattern. So when we're talking about the metals, we're going back to what we just said. So these ones in this area, these bluey ones, are likely to be shiny. They're going to be those kind of metallic colours that you know, silver, coppery, gold, those colours. Majority of them are the kind of more silvery ones. They are going to conduct electricity, they're going to conduct heat, and they're going to be malleable and ductile. Whereas these ones over here, they tend to also be solid at room temperature metals. There is one exception, which is mercury. Mercury isn't. It's a liquid at room temperature. Majority are solid. Whereas these ones, the non-metals, they are dull or colourless, a lot of them. They are not going to conduct electricity very well, and if they were in solid form, are likely to be brittle. However, at room temperature, most of them are either gases or liquids. In fact, I think they're all pretty much gases and one liquid, one or two. So that's where we're at with metals and non-metals in the periodic table at the moment. Don't worry about all these other different colours around here. This will all be kind of explained in Year 8, and knowing how these all react together will also be something that we go on to in Year 8. And as you move through to kind of Year 9 and 10, you'll start to learn about patterns and being able to work out what reactions are without seeing them and all of that kind of thing. Right, so whilst we are talking about reactions, let's talk about what happens when we do combine different elements together. Well, we get a compound. Okay, please make sure that you have written this down in your book as well. And in fact, I can't remember if I said this is the second time I did the video. If you haven't written down that, could you make sure that you do? You can pause the video now and have it there if you want, and you can add in any notes that you want to, but you need the definitions of element, atom, compound, we'll come back to in a second, and this table in your notes. So please pause the video if that's not happened. As I said, I can't remember if I said it or not because this is the second time I've tried this video. Right, back to compound. So a substance that is made of different types of atom, and the key thing here really is that they are chemically bonded together. Okay, so here's an example. We've got water over here on the left. You can see we've got two blue H atoms, which stands for H. If you look it up in the periodic table, stands for hydrogen, and one big oxygen atom. So O stands for oxygen. Okay, and you can see it's quite a nice little diagram here where I'm circling there and there. It shows that they are chemically bonded together. Okay, so they've got chemical bonds holding them together and they're not easy to split up. Now, this here is what we call a chemical formulae. This is the formulae for water. And it tells us what's in a water molecule. Okay, so we've got H2O. The 2 is telling us how many of the thing before. Okay, so this is telling us there's 2 hydrogens and then 1 oxygen. There's no number here, so we assume that if we were going to put a number, it would be 1. Okay, but we don't put it in if it's 1. So 2 hydrogens and 1 oxygen in 1 water molecule. Okay, now we talked a little bit about this one last time, or last topic, C6H12O6. This is sugar or glucose. What this is telling us is that it's got 6 carbons, 12 hydrogens, and 6 oxygens all together in one big molecule. Okay, and that's how we kind of read chemical formulae. We always put the number to the bottom right. So then we've got carbon dioxide here. C stands for carbon, and O for oxygen again, because it's the same O. You don't get different elements with the same letter. So whenever you see O, you can be sure it's oxygen. So what this means is there's 1 carbon and 2 oxygens in 1 molecule. There it is there. It's not as good a diagram because it doesn't show the bonding. Okay. Now, the only other thing to say about chemistry and chemical formulae is if you wanted to say, okay, well, I've actually got 2 water molecules, you would put a big 2 in front of it. So 2H2O, that means that you've got 2 lots of this. You would have 2 of the molecule. Okay, now you wouldn't write that. I mean, you could work out how many atoms. You would actually have 4 hydrogen atoms and 2 oxygen atoms in that case. So if you see big numbers ahead, that's another one. 2 carbon dioxide means you have got 2 lots of that. Okay, so when you see the big numbers at the beginning, that's talking about the entire thing. Okay, 2 lots of everything. It's a bit like, technically, I suppose, if you were doing it in maths, you would have brackets around it. But it doesn't work like that in chemistry. You just have to know that a big number means 2 of everything after that, and then you might have plus, and then you'd have something else. Okay, so it's similar to maths, but not quite the same. You don't need brackets and things, as opposed to the little numbers in the formulae, which tell you about the one before. So this 2 is only referring to this hydrogen, and it doesn't mean anything to that oxygen at all. Okay. Right, again, chemical formulae is something that we're not going to labour too much this year. We're going to do more on that next year. The key thing here is knowing what a compound is, that it's a substance made of different types of atoms. So if you saw a picture and it was all oxygen atoms, then that's an element. But if it was these with hydrogens as well, then that tells you it's a compound. And pretty much everything on that you know about or that you're familiar with around you is made of compounds as opposed to elements. Okay, so if you look around your kitchen, look around your bedroom, there's all sorts of different materials and they're all different types of compounds. There's millions and millions of them and only 118 elements that are the kind of building blocks for those compounds. Right, okay, so this topic then really is about chemical reactions. So when a chemical change happens, there are new substances formed, and the atoms are rearranged. So this is a nice little diagram that kind of shows that. So here we've got an element of some kind, A, and an element B. If we combine them chemically, this arrow, we don't use equals in chemistry, we use arrows like this. So what this is saying is A plus B, chemical reactions happen, we get A and B bonded together. So element, making a compound. Here we've got a compound, A and B, chemically bonded together. Reaction happens and we end up with A and B separate again. So that's kind of splitting a compound up. Here we've got a compound and an element, and you can see what's happened. This element has snuck in here and kicked B out. We're going to talk about that later on in the week. It's called a displacement reaction. And then here we've got two compounds rearranging to two new compounds. Okay, so there's other ways that chemical reactions happen, but these are just some examples really of how chemistry works. Sometimes you've got elements when there's just one type of atom, sometimes you've got compounds. Okay, and we're going to try drawing some of these types of pictures over the next few lessons. Okay, finally then, or penultimately, just before we go to the very last thing, signs that chemical reaction has happened. You might get fizzing when you react something together. Fizzing obviously is if you're going to see that if you've got a liquid. Fizzing denotes, shows kind of a gas leaving. So here's an example. You can see the fizzing's happening. There's some kind of reaction. The gas is escaping. That's what causes the fizzing. It kind of links in with new substances formed. Here's the gas. That fizzing kind of go hand in hand, although obviously if you don't have a liquid you wouldn't necessarily see fizzing. Temperature change, you could tell with a thermometer, it could lose heat or it could take heat in, so it could appear to cool down or heat up. You can usually feel, if you feel a test tube with a reaction going on, you can feel it heating up, or the ones that you do you'd feel heating up, but you can sometimes feel them cooling down. New substances formed. We've said gas would often get fizzing. Precipitate, that is basically little pieces of solid forming in liquid. So you'd see little dots of solid kind of appearing. Cool, colour change, very obvious. You notice that there's been a colour change. And smell, you often, if you've got gases releasing that have a smell, you might be able to smell them. Often you would do these kinds of experiments in a fume cupboard, so you wouldn't smell them, as particularly if they're dangerous, but it is an indication that a gas has been released. Here's an example of magnesium and oxygen reacting. I'm going to talk about that next time, but you can see a huge release of heat there and light, big energy output going on. Okay. Finally, just one thing to say about reactivity. Okay, so some elements that you find in the periodic table are way more reactive than others. Okay, what it means is that they are much more likely to react in the first place, but they're also likely to react much more vigorously than others. Okay, so they're more likely to react and the reaction will be bigger. Then, kind of in contrast to that, there are also elements that are very unreactive. They don't react at all, or not very often, and they're very unlikely to react. Now, what we can then do then is we can put the elements into what's called a reactivity series. So this is on your knowledge organizer as well. If you have a look here, these are metals. And at the top there are the most reactive metals, and down to the bottom there are the least reactive metals. These are not all the metals, it's just a selection of metals as examples. So potassium, very reactive. It's not the most reactive, but it is a very reactive metal. Down to platinum, not very reactive at all. And they're kind of in order, so as you move down you get less reactive. And next to it you can see there's a reaction with dilute acid. Now I'm going to actually talk more about this because I'm going to do this reaction for you. We need to know quite a lot about reactions with acids. But if you put potassium into a dilute acid, you're going to get a very violent reaction. And what that means is it would explode. It's likely to catch fire. Quite often if you were to do this, you would see it would react so vigorously that it would break the glass that you're doing it in. Very, very reactive. But if you put platinum into dilute acid, then you're not going to get any reaction. And what you can do is you can kind of put the metals into acid, and you can work out from how much they bubble or how violent the reaction, where they are in this reactivity series. It's a very, very common exam question for them to do this kind of thing. They might give you some information with some missing, and then they might tell you about their reaction, and you have to slot them in the right place. Okay, so down here, let's say rapid bubbling magnesium is a reactive metal in acid. You get a lot of bubbling. That is releasing a gas, you can see, and it's a lot, it's fast, that's why it's rapid. So it's releasing a lot of gas quickly. Iron, for example, though, is reactive in that it's still releasing gas, but it's much slower, it's doing slow bubbling. And right down here, lead, very slow bubbling. Okay, so it's still reacting, but very, very slowly, as opposed to sodium, potassium, which would have a violent explosion if you add them to acid, which we wouldn't do. Right, okay, let's leave that there. Give you a little bit of follow-up work to this, and then we'll get into the kind of proper reactions stuff with some examples and things next time. Right, thanks a lot, guys. Oh dear, I've lost my... There we go.